All right.
Oh yeah, here we are.
Okay. Cool. So you can hear yourself and everything?
Yeah, looks good. And there's something weird with the screen that I'm seeing here. Like not on the stream, but what I see, I have like half a window of something. Oh, like your, what is it?
On
Not sure.
on the stream?
Not on the stream, no. Just
Half
here.
a window. I don't know what you mean. Do you see something different than what's on the stream?
Yes.
Weird.
I shall show you. But it also doesn't really matter. I still see like everything that's important, I believe.
Do you see the whole notebook?
Yeah. It might be cut off a bit on the left, but I think it's fine. I sent it to you if you want to take a look at it.
Where did you send it? In the
Here in the Zoom chat. It's like half a Twitch window made its way in there somehow. I don't know why.
That's really weird. Let me stop sharing my screen and then share it again with you. Let me just share that with you.
That works. That looks good. All clean.
All cleaned up.
Nice.
Okay. All right, so let's get into it. What are we doing today?
We're still on number 4, notebook number 4. That's been the meatiest so far. And we are somewhere towards, you can actually expand on the top left. There's like this little hamburger menu in the sidebar. And then can
you
take
should
you
also
to...
just request remote control.
Oh. Preemptively? Sure. Why not? But yeah, so here you can just click.
I have to open up system. All right, I'm gonna.
Oh,
you can drive, but just from the back seat.
My arms are not that long.
All right, where do you want me to go?
So, all right. So if you scroll down a little in the table of contents, we did. Maybe we can actually revisit quickly.
We did this
just by looking at. Yeah, this is what we did last time. Before second to last time, we did the whole digit stuff and trained like a naive model on it. I guess just looking at the average of all the images, and then we started last time. We thought about stochastic gradient descent. You hear how I said we thought about, not we learned about.
Yes, we did think about it.
We definitely did think about it, so that's something.
You don't feel like you learned anything last
Sure, I learned something, but I don't have the feeling I learned stochastic gradient descent. That's a bit. That feels like a little far.
A little bit of a stretch.
Yeah, to claim that, to claim knowledge over this topic. So I shall not. I shan't.
Shan't. Fair enough. Fair enough.
But yeah, I learned something. Sure. Slow process, step by step.
All right, so
now we want to like skip all of this, right? Because we already thought about it.
These are all like buzzwords from years ago when I actually took a course on this.
What? Stop?
Sigmoid.
It's just a function shape, right?
I believe so.
All right. So yeah, we've got, I think, 64 cells in the MNIST loss function and another 20 something in putting it all together. So let's grab this 04 by the hair and start going. Click away this table of contents. I want space and focus. Gracias.
Should I guess until somebody, should I make this, the window bigger in the stream? Also?
Can you like swap that around easily? Then yes.
Yeah, I can swap it around. Can make it
Okay, cool.
super big.
I mean, you could also just have this chat, overlay, and it's not that readable, but whatever.
That's what it is now. I mean, if somebody jumps in and wants to talk about it, like it's here, regs.
Yeah, I did.
Okay, I think we didn't do any of this yet. I'm just gonna go click back into this. Wow, it's very slow today.
Oh yeah, our computers have decided that it's a slow day today, both for the internet and not for heating up. That's the only thing. It's fast today.
Where?
Fair enough.
Did this start?
What you looking for? Oh, the start.
Yeah.
There. Okay.
When I close a table of contents, it shifted everything up.
Okay. Can you just scroll a little up? Then we see that we're actually hooking onto what we stopped last time. Because I don't. All of that we just saw can be transposed directly onto. Yeah, we did that. Okay. Nice. What was the couple of steps that everything should go through? Nick, you remember? There was this like 7-step process or something. I know the last one was stop. Stop when we decide that it's trained long enough.
I do remember that one. Hold on, I'm just checking, make sure that this is okay.
Yeah, change around. Yeah, you got it. Also, when you click on this RAM disk thing, it gives you a modal pop-up that tells you where you're at. Whether everything's running in the right place. Yeah.
Nice. I like the way you say modal.
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 If you say modal, how do you say it?
Modal?
Modal. This sounds so Styrian, like heavy Austrian accent, South Austrian accent. If I say modal. So it's not modal.
I like
modal.
I like modal better.
All right.
And I may just start saying it that way.
Modal.
The modal. All right. So, all right. So let's get into it.
Let's do it. Do you want to start? I can start. You want to start? Who starts? We should do scissor paper.
Rochambeau.
Yeah. One win. Ready?
Okay.
1, 2,
3.
Wait. Okay. Pause. Let's do it again. All right. Ready? Okay. 1, 2, 3. Okay. 1, 2, 3. Okay. 1, 2, 3. Are you waiting for me to do it?
No,
okay, whatever.
No. I'm doing it, and I'm looking at you, and yours. I think
because
you're
it's
waiting. So
I thought you were lagging.
There's definitely a lag, but I thought you were waiting for me. I'm just.
Well, yeah.
Anyway, whatever.
Anyways, I lost. So what does that mean now? Do I start or do you start?
We didn't even figure that one out. So, anyway, all right. Let's. I'll start. I'll start.
Okay. Proud winner.
Only because after I go through this one, I'm gonna get up and get a water because I forgot to get that before I sat down.
I see.
So if you need to get a water.
No, I'm gonna listen to you. I wanna know what you're reading.
Ooh.
I wanna learn from you.
Not just observe stochastic gradient descent. All right. The MNIST loss function. Sorry. So we already have our dependent variables x. These are the images themselves. We'll concatenate them all into a single tensor and also change them from a list of matrices, a rank 3 tensor, to a list of vectors, a rank 2 tensor. We can do this using view, which is a PyTorch method that changes the shape of a tensor without changing its contents. -1 is a special parameter to view. That means make this axis as big as necessary to fit all the data. Okay, so train x torch.cat, stacked 3s, stacked 7 views. Okay, so there's that -1, and then 28 by 28. Should I run this? Probably.
Gonna have to run everything beforehand. But I think there's you can do like a run everything beforehand. I think it's in runtime. Run before. Yeah.
Clicked it.
You're gonna have to do the authentication bit at the start if you haven't. You know, this one.
Oh, jeez. Hey, Space Rest.
Oh, hi. Thanks for tuning in. You can copy Nick's password. I think it's a one-time thing, but
First of all,
who knows?
It's our password.
Oh, right.
Shared account.
Oh yeah, don't copy it.
Okay, so all of this should have ran. I'm just gonna go back to this.
Yeah, I think it should be pretty quick.
This is so slow today.
All right, no, don't do that. It's gonna do everything again.
Yeah, but it should be fine.
Yeah.
Oh, you're saying it actually ran everything.
I think it did probably. It just had to run that last part, the last cell one more time.
All right. Let's see.
I feel pretty zen about not having the power today of scrolling. Maybe it's gonna be much calmer because I just keep flipping up and down all the time usually. Maybe it's better like that. I'm just gonna relax and give audio like tips every once in a while.
There we go. All right, cool.
Yay.
So we need a label for each image. We'll use 1 for 3s and 0s for 7s. Okay.
Why not 3s for 3s if it's just a label? Just saying.
Do you want me to change it?
No, I'm just
Change
saying.
everything?
Maybe. No.
All right. A dataset in PyTorch is required to return a tuple or tuple. Do you say tuple or tuple?
I say tuple.
I say tuple also.
Yeah.
But you also say modal.
I also say modal, so. Which one?
Tuple?
Tuple?
Spell it out.
T-U-U.
Tuple.
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 That's oh, I see. See, I read that as tuple too. So I guess. And what about modal? Is it modal or modal?
I think most people say modal.
Yeah, probably. Everyone who knows English. No idea. Okay.
All right. A dataset in PyTorch is required to return a tuple. I'm gonna just interchange tuple and tuple to make everyone happy. Of x, y when indexed. Python provides a zip function which, when combined with list, provides a simple way to get this functionality. Okay. So what's happening here? List train x, train y. Okay.
That's making a list of tuples.
Mm-hmm.
You hear that? Yeah, all right. We know about zip.
what's happening here.
Torch cat.
Are all the valid ones and doing the same thing. Valid data set. Okay. Now we need an initial
I
random.
just spaced out. Is that did you? What happens in the piece of code?
It just seems like it's doing the same thing. It did these with the training set, and now it's doing the same thing with the validation set.
Well, what? Okay. Keep going.
Good.
I'm not really following along right now, but I think I'm gonna come into it.
You're just too zen. Maybe we do have to
letting things flow today. Things are just flowing. It's
maybe
good.
we do have to give you
All
control. All right. Now we need an initially random weight. Okay, for every pixel, this is the initialize step in our 7-step process. Okay.
I remembered it was 7 steps.
And you remembered one of them.
Yeah, we just stopped.
Stop when you get bored. All right. The function weights times pickles. Weights and pickles won't be flexible enough. It is always equal to 0 when the pixels are equal to 0, i.e. its intercept is 0. Okay, you might remember from high school math that the formula for a line is y equals w times x plus b. I knew it as mx plus b, but w is fine also.
I know it like a mx plus k, I think.
Yeah. We still need the b. We'll initialize it to a random number too. Okay, so b. In neural networks, the w in the equation is called the weights. All right, so at least this sort of makes sense.
That's
the
consistent,
bias and the weights. And the b is called the bias. All right, together the weights and bias make up the parameters. Jargon, parameters. The weights and biases of a model. The weights are the w. Okay, so we just went over that. You can now calculate a prediction for one image. Okay. Train x, 0 weights, t dot sum plus bias.
Oh, it's this function thing again. Remember?
Yeah.
Add backwards 0. So there's a plus somewhere in there. I sum. I guess the sum.
I think we left something.
Plus.
I wonder if we're gonna realize at some point, because I ran everything above, and I'm assuming it's not super cleaned up and ready for the MNIST function, then maybe we should.
You think that
the way it was.
we messed something up?
Well, I just don't know how they like feed into each other. So if in like 20 minutes when we are through this section and we realize something is not adding up, I think it's because we we'll just revisit the gradient descent. Anyway,
We'll keep that in mind.
Keep it in mind. Could be wrong. While we could use a Python for loop to calculate the prediction for each image, that would be very slow because Python loops don't run on the GPU. And because Python is a slow language for loops in general, we need to represent as much of the computation in a model as possible using higher level functions. Okay. In this case, there's an extremely convenient mathematical operation that calculates w times x in every row of a matrix. It's called matrix multiplication. Shows what matrix. Oh, this open close weird thing. Looks what it is. Okay. Do you understand the concept of matrix multiplication?
Yeah.
Can you explain this to me?
It's just my understanding of it is that it's just if you have two things, you multiply always the rows times the columns, like every item inside of it times the item inside of it, I believe. But let's look it up. I'm not a.
So I was gonna say like A1, B1 should be here. A1,
yeah, but
2,
like
B1.
Yeah, but then the way that this graphic looks like, it looks like both of these go into one cell. So A1 times B1, maybe plus A2 times B2 or something. I think maybe go for this math is fun or something like that. But I have the feeling it's not that hard of a concept. Maybe I was wrong. Okay, so 2 times you just apply it to everyone, every single one, and then if you have 2 matrices, yeah, it's row times column, right?
This is what?
First row times the first column, yeah.
So this
then
is everything in the first row? So is this the sum?
Dot product. A matrix by another metric, dot product, first columns directly answer. First row and first column.
Okay, so 1 times 7. Okay, so it's 1 times 7, 2 times 9, 3 times 11, and then the sum of that.
And then 58. Add it up.
Got it. Okay.
And then you do the next thing is then the first row times the second column, right? Yeah. And then second row times first column, and second row times second column. Which is always just each individual item times and then adding them together, I guess, right? Yeah.
Yeah, and then, so what if...
And they always have there's this thing about what shape do they have, like a result matrix, and it's always the...
I get it here, yeah, like this is smallest. A single row.
Yeah.
This is 3, but it's got 4, so it's going to come back with a single row with 4 columns. Yeah, okay. I got a pretty good understanding of it. Sweet. Okay, each item of the result, which we'll call AB, contains each item of its corresponding row of A multiplied by each item of its corresponding column of B. Okay, add it together. Got it. For instance, row 1. All right, we just went over this. Nice. Now it's your turn, Martin, to be like, hey, Nick, scroll down a little bit. Maybe you'll get the answer.
I trust that you're going to think of that.
You did trust me. I let you down. Sorry. All right, so
actually, can you scroll up a little? What's this? Is that in Python matrix multiplication is represented with the add operator? I've never seen that before. XB add weights. That's interesting. I didn't know that operator. Surprise. Is that like a general Python thing, or is this a NumPy thing? I don't reckon you really operate with matrices much in normal Python, but probably a lot in NumPy.
Yeah, I mean, we could try it, but it's going to take a bit of a setup.
No, not really. You could just try. Oh yeah, it does take a bit of a setup, huh? Do you want to try it? Or just Google it? Add operator. Right. Nick dives into writing Python code for the first time in
5
XB add weights years.
Wow.
Google pronunciation thing. When I googled how to pronounce tuple, animated mouth. Oh, seriously?
Okay.
Can you check that out too?
Check what out?
Space Rest just wrote that there's that the Google pronunciation thing has an animated mouth now.
Well, that takes
precedence clearly.
Oh, that's weird.
Yeah. Wow, interesting. That doesn't really tell you much though. It's just like opening and closing it. You don't really see much of a tongue. Oh, you can practice speaking it. American pronunciation. Okay. Is there a way you can see into the mouth or something? Or like what she's doing with what this what this thing is doing with the mouth? Nice. Modal. Modal.
Interesting.
Modal.
This is like super off topic, but have you been on, there's this like YouTube channel, I don't know if it's this one, pronunciation guide, but there's one, yeah.
Where one?
Okay, so this one, all right. So this one, so there's two pronunciation guide. Oh man, there's these two channels on YouTube. One was like created to actually teach people who are learning English how to pronounce words properly, and then somebody copied the same YouTube channel with very similar name and just really like butchers these words, but like so seriously. Like the word Chipotle is like Sean Tootle. And that's like the entire video. And there's so many like Jake Gyllenhaal's name. Like it's so they really like butcher all the words. It's so great. It's definitely recommend rabbit hole for YouTube. Anyway, and that's the one that does the poor pronunciations is the one that's verified on YouTube. The original one that's trying to help people. Yeah, it's totally a parody, but that one is certified and the other one is not, or verified or whatever. That like little check mark you get at after your name. It's so funny. Anyway, it's great. Moving on. All right. The first element is the same.
Wait, you wanted to do some other rabbit hole on the Python, Nick writes Python code rabbit hole.
Okay, so you're going to have to excuse it because I'm still on Python 3.6. I don't know what, are we on 4 yet?
That's all right. No, we're at 3.8, but 3.6 is fine. Anything above 3.6 is fine.
So tell me if I'm doing this properly. And then here, we're just going to...
So far, yes. You're making a list. Was that going to be a list of lists?
Yeah. This is how you do it, right?
Well, I'd say so, yeah.
Okay, and then what is it? Oops. A
Should be
at
fine.
B.
Uh-huh. All right. Unsupported operand types for at list and list. That makes sense to me, but then maybe it's actually so try now inside of the notebook. Just make a new code cell in there and try with two maybe NumPy arrays. You could just make 2 NumPy arrays because we got just transform those lists into NumPy arrays. I think it's probably like something like np.array, and then you just pass in the whatever here you have.
Okay, so wait.
You could just wrap it around the list when you make them. This is not going to work, yeah. Mm-hmm.
So what do you want me to do? np.array right here?
I think so, yeah. If that's... Mm-hmm.
Whoops. Like this?
Yeah, exactly. Input operand 1 has a mismatch in its core dimension 0 with gfunc signature n question mark k comma m question mark. n question mark m question mark, size 2 is different from 5. So but that actually means that it recognizes the operand. So I assume it's something that NumPy has implemented, maybe, because pure Python doesn't seem to have it.
Interesting.
And it's saying that you can't multiply them because they have a different size, I think. Yeah, because I only know the add operator from decorators, which is like some functions wrapping functions.
Look at real Python.
Yeah, I don't think there's any, because there's no matrix, there's like no matrix data type or anything like that in pure Python. Search me with NumPy or something, and then add operator. Just saying.
So that's using NumPy. This is just saying to do the dot.
Dot. Okay. Is there any add in there?
I didn't see. We use the add operator. Okay. So
that's, but does have the same input sizes, it seems.
Yeah.
So and were they NumPy arrays?
Mm-hmm.
Okay.
So if I do np dot, I should get the same error, right?
If it's just a shortcut, yeah.
Mm-hmm.
Shapes, it's not the same error, but
different.
So it seems to be calling something else.
If I just wrap this, is it going to make it go away? No.
You'd have to have two inner ones too, right?
Mm-hmm. And do they have to be the same length?
I'm not sure. Shapes 2, 5, 2, 5 are not aligned. If dimension 1 is not dimensions.
Interesting. And they are the same shape and the same size.
Is that maybe the second one has to have, like, if you have 2 rows? No. Yeah, if you have 2 rows, maybe the second one has to have 2 columns. What if you only have 2?
You're saying like this?
Maybe I'm saying like that.
And then how many? 5 of them? 1, 2, 3.
Yeah, I would have just deleted some and make it 2 times 2 for easiness sake. Easiness.
Okay, so that's...
Oh. Okay, so wait, so that's part of matrix multiplication stuff, right? So we said the rows, everything inside of a row that goes this way, every item in a row gets multiplied with the corresponding item in the column, right? So if you have to have the same amount of items in a row that you have in the other metrics that you have rows for this multiplication to work, right? If it's like 2 rows of 5 items, then the other one has to have 5 rows times 2 items.
I don't think it should be like that, though. It seemed like it could work. Yeah. I guess I didn't.
Okay, so now we have... Okay, if we drizzle that apart. Yeah.
So it seems like this is a column. No, this is a row. the number of rows need to be equal to the number of columns, right? No. Because if I remove this, yeah. So it needs
1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And those are. Wait, so you got one big, like you have one outside bracket, and then inside two.
It seems like the amount in here needs to be equal to the amount of arrays inside of that.
Bro.
So if I remove this, it should work. Yeah, with just one. But at the same time, what happens if I...
So you could have an endless amount of these. So yeah, that makes sense. That the row dimension,
right?
The row dimension has to fit the column dimension, right?
The row dimension needs to fit.
Like that, the amount that's stacked in the first matrix like that needs to fit the amount that's stacked in the second matrix like that. So that this, so that this multiplication stuff works. You know, that like you can combine one with the other.
So if I do 1, 2, 3, 4.
Yeah, I think
5,
that's a rule
6,
in
7.
matrix multiplication. If I dimly remember. Yeah.
They should work and just come.
They should work,
okay.
Yeah. Just goes bigger.
Cool. I think I sort of get it.
Nice.
So we've learned 3 things today.
What were they?
Where was it? How to say modal? How to say tuple?
Modal. Tuple. Modal. Matrix multiplication.
Yep. Thank you, everybody. That's the stream. It's enough for my brain to process this week. All right. So then let's just, so in Python, okay. And then the first element is the same as we calculated before, as we'd expect. This equation, okay, is one of the 2 fundamental equations of any neural network. The other one is the activation function. All right.
Batch matrix multiply with weights plus bias.
Okay, so let's check our accuracy to decide if an output represents a 3 or a 7. We can just check whether it's greater than 0. So our accuracy for each item can be calculated using broadcasting, so no loops. Cool. Okay, so predictions.
And that works because we assigned 7s are going to be 0, right?
Right, so this is saying, so
that's just the labels. It's just looking at the labels, and because we made the labels be numbers, 0 or 1, we can just say if it's bigger than 0, it's going to be a 1.
Sure. So I guess what I'm just asking is, like, it's going to go through each of these elements in this tensor, and then if it's greater than 0, replace it as true. And then what is this?
No, I don't. Is that the prediction tensor? Can it go up again?
Okay, wait, hold on. So prediction, preds is the tensor. And then
is that what we looked at above? It contains these numbers?
Yeah.
Huh.
So what's happening here, right? It's not looping. I don't know what broadcasting is. Is that a Python?
No, it's a I guess it's like a PyTorch or whatever. It applies it to everything inside of the batch. It's kind of like doing a loop, just without a loop. I don't know how it works, but
okay, whatever.
That's what it does. Yeah.
Cool. So here it's just saying.
Can you print out predictions again just above that?
Yeah.
Because the output that we saw before didn't have the second to last one wasn't below 0. So that's kind of confusing unless it shuffles it. What's train Y? Yeah, you can just try printing it.
Yeah. Oh. Oops.
Yeah, okay. So these are the labels that I thought about before. Correct. So, okay, so it's comparing. It's comparing, it's taking the numbers that are in the predictions, comparing whether they're bigger than 0, and then making a float out of it. That would mean whether prediction is 0, that's I guess it's true or false. And then it makes a float out of it, so it's going to be 0. That's weird. Can you can you play a bit more with this and do like predictions? I don't know, one item of predictions, maybe the 0th or something. Dot float.
Yeah.
What that does. Okay, and what if you do the exact thing?
Do I have to print both?
Yeah, it only shows the last one. Yeah. This one you don't have to print. The last line it prints automatically.
I know, but if we're going to write stuff, okay.
So try this predictions bigger than 0. Bigger than 0, 0. Like the way that it's written down there. I think it's predictions. I just take the first one. Predictions at the index 0 is bigger than 0.0 and then dot float.
Okay, so.
And then without the equals train Y at first. I'm interested what that does.
1.
Interesting that it didn't break, even though you have a weird bracket there at the beginning.
Why?
Because. Oh, no. Sorry, it's closed. I didn't see that. Oh, good. Okay, so 1.0, which means it's bigger than 0. That's true. Like predict the bigger than 0 must return true, and then it converts it to a float. And then it compares. Because 1 is truthy, so you can compare it to. So you can compare 1.0 to true, and it's going to be true. And you can compare 0.0 to false, and that's going to be true. Makes sense. But it's a interesting way of writing it. What are you doing right now? What are you trying?
I'm just
cleaning up.
No, I mean they should be above the. But anyway, I'm just looking.
Can you just print also just the predictions at the space 0, like at index 0 is bigger than 0.0? I think that should return 1, like without doing the float at the end. The last line of code, just without the float. Which should just be 1. Because it's bigger than 0.0, like it's 5 point something, so it's bigger than 0, so it's true. Right, so that's the thing. So it's true, and then you're converting it to a number.
Got it.
And I don't understand why it's converted to a number though, because you could just compare it to train Y, which is also a Boolean, right? If you would do in here now equals train Y at index 0, it should be the same.
Yeah, train Y at 0 is.
As far as I know.
Oh, it's 1.
Oh, it's 1. Okay. Okay. But Okay, I see.
Yeah.
Yeah, because our labels were 1 and 0, not true and false.
Right here.
Okay. Yeah, right. Okay, yeah. Weird way of setting it up, but
Probably really smart.
probably.
Okay. So now we're going to change one of the weights and then do the same thing, and then we're going to compare these two numbers, I guess.
Change in accuracies for a small change in one of the weights.
Okay, this actually changed nothing. Actually, we haven't seen that we need gradients, because apparently they don't change anything.
You ran them both? Yeah.
Yeah. Go crazy. Same thing.
Wait, that's suspicious. May I say? Wait.
Oh, I have to run the bottom one. Right?
Yeah, you have to run that too.
Oh, it's the same.
Well,
it's the same.
so that's. I think that's kind of suspicious.
Man.
Okay, interesting. Can you leave a note in there?
Oops.
Track 6.
How do you this way? Is that comment in?
No, it's a hashtag. Is it go comments or double slash?
Yeah.
Yeah. So why is that not? Is that supposed to actually linear 1? What was linear 1? Is that something that we set up and maybe didn't set up? Are we at the 20-minute mark where
we are
just
kind
running
of like
all of the code cells before?
Yeah. No, linear 1
Okay.
is here.
Do you run that?
Yeah.
Are you sure?
No.
Wait, it looks like you did.
No, this is nothing. That's nothing.
That's also just us playing around. So that was linear 1.
I'm just gonna
Yeah.
the same number. Change the weights drastically. And we get the same exact thing. So linear 1, train X,
Train X.
train Y, everything else is, and
Train X and train Y should be no. One of them should change. So X are the images, right? That's not gonna change. And Y is the label, so should also not change. So what's linear 1 again? Return
XB times
XB
weights
times
plus bias.
extend matrix times weights plus bias.
Oh wait, did I change something? No, we have.
We must do some new training when we change the weights. Otherwise, of course, it's going to be the same, right? If like there wasn't any training that I understand, at least.
So it's not in that. It's not there.
You're way up. This is already last stream. Yeah, that's the point. Get it? Smart.
I'm not sure that we did have train X and train Y here. Because we were dealing with this like params.
This lesson goes way up, you know?
Yeah.
We did all the... because now we're going back to the MNIST dataset, actually. So this is probably related to MNIST training that we did early on.
Is there a way to see where
Search.
this is?
I think you can just search normally, like
Yeah.
as a website search. There. Torch the cat.
Oh, so
Don't
this
touch
is
the
for
cat.
today.
That's
This is
from today,
so-
yeah.
And then train Y is this tensor. Okay.
But let's stay there for a second. So torch category stacked 3, stacked 7's view. Okay. Training data. That's just getting the images. And then train Y, tensor, length 3's. That's just, yeah. Okay. All right. Maybe we should heed our own
Let's see.
Let's read forward.
Okay.
As we've seen, we need gradients in order to improve our model using stochastic gradient descent. And in order to calculate gradients, we need some loss function that represents how good our model is. That's because the gradients are a measure of how that loss function changes with small tweaks to the weights. So we need to choose a loss function. The obvious approach would be to use accuracy, which is our metric, as our loss function as well. In this case, we would calculate our prediction for each image, collect these values to calculate an overall accuracy, and then calculate the gradients of each weight with respect to that overall accuracy. Unfortunately, we have a significant technical problem here. The gradient of a function is its slope or its steepness, which can be defined as rise over run. That is how much the value of the function goes up or down divided by how much we change the input. We can write this mathematically as y new minus y old divided by y new minus y old. X, yeah, that would make sense. Y new minus y old divided by x new minus x old. This gives us a good approximation of the gradient when x new is very similar to x old. X new, x old, meaning that their difference is very small. But accuracy only changes at all when the prediction changes from a 3 to a 7 or vice versa. The problem is that a small change in weights from x old to x new isn't likely to cause any predictions to change. So y new minus y old will almost always be 0. In other words, the gradient is 0 almost everywhere. Okay, so maybe it was expected that it didn't change. Scroll, please.
Oh, whoops.
Oh, good. What were you thinking about?
I was just changing how the chat is overlaid on OBS because it was like blocking.
Because you know all of this already.
Yeah.
Yeah. Come on.
Come on.
A very small change in the value of a weight will often not actually change the accuracy at all. This means it is not useful to use accuracy as a loss function. If we do, most of the time our gradients will actually be 0 and the model will not be able to learn from that number. In mathematical terms, accuracy is a function that is constant almost everywhere, except at the threshold 0.5. So its derivative is nil almost everywhere and infinity at the threshold. This then gives gradients that are 0 or infinite, which are useless for updating the model. Okay. Instead, we need a loss function which, when our weights result in slightly better predictions, gives us slightly better loss. So what does a slightly better prediction look like exactly? Well, in this case, it means that if the correct answer is a 3, the score is a little higher, or if the correct answer is 7, the score is a little lower. Let's write such a function. What form does it take? So what form does it take? I guess we need to look at the pred, at the predictions variable, right? And then just figure out some cutoff value of like, is it, no, we want to figure out what changes the prediction slightly. This is what we want to do.
So, I mean, let's keep reading.
Let's write such a function now. What form does it take? The loss function receives not the images themselves, but the predictions from the model. Yeah. Let's make one argument of values between 0 and 1, where each value is the prediction that an image, where each value is the prediction that an image is a 3. It is a vector, for example, a rank 1. No. What does IE stand for? In examplus, I eat rank 1 tensors. You can also learn how to pronounce it. It est. Meaning that is. It est. It est. Can you do pronunciation it est so that I can see the mouth moving? Oh, we don't get it.
Sorry.
Why's that?
Sorry.
Because it's 2 words, maybe. Est. It est. Okay, we can do it. It's fine. It est.
So I actually was looking at this, the difference between IE and for example, and when to use it, because I think they're like a lot of people use them interchangeably, but they're not. Like IE. What did I just? Oops. Come on. Ugh. I don't know what's happening. I tried to reopen. That is something previously mentioned.
It est, i.e. Yeah. And people use it interchangeable with e.g.
Right.
Which I also don't know what it stands for. Examplus given. Example given.
Let's see.
Exempli gratia. All right. Got some nice Latin in there. Yeah. For example, yeah. No one does FE though, right? Like you don't abbreviate in English. You don't do F.E.
No, what is that? Element iron.
No, I just meant for example. Element iron.
All right, I'm done with this.
Right. Okay, IE. All right, rewind. The loss function receives not the images themselves, but the predictions from the model. Okay, let's make one argument of values between 0 and 1, where each value is the prediction that an image is a 3. It is a vector, as mentioned previously, a rank 1 tensor. It's true. That's what it is. We mentioned previously that a vector is a rank 1 tensor. So it est makes sense here.
Yes.
Indexed over the images. So it is a vector indexed over the images. A rank 1 tensor indexed over the images. Value is the prediction that an image is a 3. It is a vector. Okay, so we got all these numbers going over all of the images, and for each image there is like one entry that is like the prediction of whether it's a 3 or not. The purpose of the loss function is to measure the difference between predicted values and the true values, that is the targets, aka labels. The purpose of the loss function is to measure the difference between predicted values and the true values. Okay, yes. Let's make another argument with values of 0 and 1, which tells whether an image actually is a 3 or not. It is also a vector. It est another rank 1 tensor indexed over the images. Okay, yes. So we have the predictions and we have the labels. So for instance, suppose we had 3 images, which we knew were a 3, a 7, and a 3. Suppose our model predicted with high confidence 0.9 that the first one was a 3, with slight confidence 0.4 that the second one was a 7, and with fair confidence 0.7, but incorrectly, that the last was a 7. So it means that our loss function would receive these values as its input. Targets tensor 1, 0, 1, that's just the labels of what is what. Predictions tensor 0.9 for the first one, correct, 0.4 for the second one, not correct, 0.2 also not correct. Unless, I guess, we actually only have a function that predicts whether stuff is a 3, not whether it's a 7, if I remember correctly, which is saying if it predicts that it's not a 3, then it's a 7. So I guess 0.4 in the second one just means it has low confidence that it's a 3.
Okay.
So that would be also a correct prediction. Okay, here's a first try at a loss function that measures the distance between predictions and targets. MNIST. Oh, hello. Someone did 2 lines for a function, huh? Define MNIST loss predictions targets. Return torch where. Torch.where. Thank you. Making it harder for me. And I don't have the power to change it. Thank you.
There you go.
My wishes have been heard. Okay, return torch.where targets equals 1 minus predictions dot mean. Torch.where, I guess that's some sort of functional programming thingy where it applies it across. How's that? What was the function doing? Targets equals. Okay, so where the target, okay, we're passing in the predictions and the targets. Where the targets are 1, that means this is meant to be a 3, should be a 3, and then we have 1 minus predictions. Okay, so we get a value between 0 and 1, and then the third one is predictions. We pass in predictions. I don't know why. And then we take the mean of that. Do you understand that better? What's that? So targets, I kind of understand that targets equals 1 and 1 minus predictions, but why is predictions in there? Any thoughts? Nick thinks quietly, unlike moi.
Let's see.
I mean, so this is supposed to be our loss function, so it should give us an output. I mean, I guess we should know what .where does. Or just straightforward. Yeah, torch.where, right? That's what I was just wondering about. Do you want to run this help torch.where that they're suggesting, so we can figure out what's going on in this?
Yeah.
Or just read. We're using a new function torch.where ABC. This is the same as running the list comprehension B at the space of I if A at the space of I, else C in the space of I for I in range length A. Except it works on tensors at C/CUDA speed. In plain English, this function will measure how distant each prediction is from 1 if it should be 1, and how distant it is from 0 if it should be 0. And then it will take the mean of all of those distances. Nice. With the docs, it's important to learn about PyTorch functions like this because looping over tensors in Python performs at Python speed, not CUDA speed. Try running help torch.where now to read the docs for this function, or better still, look up in the PyTorch documentation site. Help torch.where. Okay, so where condition x, y. So condition was the targets are going to should be 1. That's our condition. And we have x and y as input, and it returns a tensor. Return a tensor of elements selected from either x or y, depending on the condition. The operation is defined as arguments. What's the math definition here? Text curly braces out underscore I. This looks very confusing to me.
I don't know why, but is this a big cell or something? No, not really. Oh, it's like an internal scrolling cell. So scrolling was like janky.
Mm-hmm. Yeah, you can scroll in there.
Yeah.
Right.
So does this how distant each prediction is from 1 if it should be 1, and how distant from, then it will take the mean of those distances. I mean, it's pretty straightforward.
Yeah, I mean, I guess the functionality in there is nicely explained in real words, but help is not that easy, not that straightforward for me.
Okay. All right, so you can see this function returns a lower number when predictions are more accurate. When accurate predictions are more confident, hold on, lower number. You can see this function returns a lower number when predictions are more accurate. When accurate predictions are more confident, and when inaccurate predictions are less confident.
So we got three reasons when it returns a lower number, right? When predictions are more accurate. So, okay, so it's a lower loss if the prediction is pretty good. Like it's predicting it's a 1, it's predicting it's a 3 with 0.9, so that's a very high accuracy.
Sure.
And then it returns a low, like it's gonna return 0.1, I guess, or something like that. Probably the difference to 1, I assume. So it's returning a low prediction in that case. When accurate, so that's case number 1. Then we have case number 2, when accurate predictions are more confident, high absolute values. Okay, again. So that's just if it's 0.7 accurate prediction versus 0.9, then it's going to be a lower number if it's 0.9, if it's more accurate. Right?
I don't know. I think I just...
And when inaccurate predictions are less confident. So that would mean inaccurate prediction. So it's saying, okay, so it's saying it's a 7 with 0.4. No, that would be 0.4. Would assume it's a...
I don't think these numbers... Actually,
right. No, I'm just using them as to think them out. They're just related to whatever the probabilities were that we punched in before. Okay, so three examples. We get lower loss. In PyTorch, we always assume that a lower value of a loss function is better. That means it's like a better fit. It actually was. Since we need a scalar for the final loss, MNIST loss. Scalar is just one number. MNIST loss takes the mean of the previous tensor. MNIST loss, predictions, targets, tensor, okay. Predictions, targets. For instance, wait, what was that? Where did this MNIST loss come from?
This is the function that we just created, no?
That we just wrote, okay, gotcha. Okay, and we're passing in those two, yeah, right. And it does the mean in there in the function.
Yeah.
Okay, all good. Cool. For instance, if we change our prediction for the one false target from 0.2 to 0.8, the loss will go down, indicating that it's a better prediction. Makes sense? So the last one was a 3, and we falsely said it's not a 3, but now we're more confident it's a 3, so the loss overall is lower. One problem with MNIST loss as currently defined is that it assumes the predictions are always between 0 and 1. We need to ensure that this is actually the case. As it happens, there's a function that does exactly that. Let's take a look. Scroll. All right. You want to go?
Sure. The sigmoid function always outputs number between 0 and 1. It's defined as follows. Okay, return 1 divided by 1 plus torch exp minus x.
Oh, now it suddenly makes sense. 1 plus torch.exp minus x. I wonder what torch.exp is. Help? Let's do it. Let's read some hard to read documentation.
You can't just like hover over and they give you the gist of it or something?
You can also do doc torch.exp, I think. Oh yeah, just hovering sometimes might work too. Input times turns a new tensor with the exponential, exponent of the elements of the input tensor. All right, that was actually helpful. Okay, so we're doing some sort of, is that like what's it called? The quadratic loss function. Is that something like that? Because we're giving it a negative x as input, but making a square thing.
I don't know. I need some water or something.
Oh, all right.
Take two minutes. Do you want to scroll?
I gotta 2 minutes. What am I gonna do for 2 minutes? We can have intermission. I can also get some water. No, keep going. I'm gonna look around this.
You want to do 2 minutes? You want to do an intermission? I'll put the waiting screen back on. We should create an intermission screen with a countdown of 2 minutes. All right, I'll be back.
Yeah, right. I'm gonna. No, wait. Give me. I can't scroll. Oh no. Oh no, Nick is gone. I don't have. Oh dear. All right, so I don't actually have access to the screen, so I can just sit here and do nothing. Let me muse a little. PyTorch defines an accelerated version for us, so we don't really need our own. It's an important function in deep learning since we often want to ensure values are between 0 and 1. This is what it looks like. Plot function, torch, sigmoid, title, sigmoid, minimum -4, maximum 4. Return 1 divided by 0, whether I can understand a mathematical function. Return 1 divided by 1 plus torch. What's that even called? To the power of. So we're passing in a value, taking the exponent of the negative version of this value, which should make it positive. And then if it's positive, yeah, but we're not taking square root out of it, it seems, either. And then we do 1 divided by 1 plus this exponent. And that builds this beautiful curve. I wonder why. Hi, Nick. Nick is back.
Hello.
Hey. I couldn't control the screen, so I was stuck on here, which is not a problem at all, because it's not that I understand what's going on.
All right.
Do you understand the maths that's going on up there, and why this makes this beautiful sigmoid curve? If you go so it's taking the negative of the variable that you input and putting it taking the exponent of that, right? Which should make it positive, and then you do 1 divided 1 plus that. Why does that make this pretty curve?
Okay, so let's
move on.
No.
What's going on out there?
I don't know. Police.
Good stuff.
Ambulances. Fire trucks. The sounds of New York City. Do I understand this?
Did you just run it and it changed the shape of the function?
You did
that. I see. Yeah.
It seems like it's all the same.
But this is different.
Which?
The original one.
Well, it's the same. It's just like as it gets greater and greater, it's just reaching 1, but it never reaches 1.
Mm-hmm. Mm-hmm.
Oh, here, I guess this changes. This.
Right? No.
No.
Huh. Any thoughts?
Oh wait.
I'd like to better understand this curves.
So this is our defined function, but we're using PyTorch's sigmoid function to plot this. That's why whenever we change this, nothing happens.
I see. So what if you change it and then you, instead of doing torch.sigmoid, you actually put in sigmoid?
Yeah, that's what I'm gonna do.
Okay, cool.
I'm gonna plot. Oops. No.
Bye.
Oh, God.
Where'd you go?
I don't know. There we go. So
Okay.
that's the same.
That's different. Is it? I think it's a
Slightly.
little different.
It's
Yeah.
curving up higher here.
Yeah.
Yeah,
That's different.
it's very different. Okay, so I don't fully understand the math.
We should take a math course.
We should. We definitely should.
Take a math course. Come back to it afterwards again. To a second round.
So, all right, I'm just gonna skip. So,
Wait, what? You skipped all of it?
no.
Then-
We're on the last one. There's this little few paragraphs here.
Yeah.
And then we go on to the next section. So, what are you suggesting? You want to take a math course and then revisit this whole section, like as a review, or?
Oh, no. I wasn't. I was just saying that. I meant more like we should take like a proper math course at some point, you know, and then just do everything, do the whole course again. It could be fun. That's like a very future plan. It's like a within the next 2 years kind of thing.
Got
Not,
it.
let's do it now.
Got
Yeah.
it. Okay.
That's what I meant.
All right. So then let's continue this.
Yeah.
Okay. It takes any input value, positive or negative, and smooshes it onto an output value between 0 and 1. It's also a smooth curve that only goes up, which makes it easier for SGD to find meaningful gradients. Okay. Oh, is this never mind. Let's update MNIST Loss to first apply Sigmoid to the inputs. Okay. So predictions.sigmoid, so it's applying it there, and then
So it's actually using
grabbing the
our
mean. Yeah. It's
Right?
using our one. Yeah.
our Sigmoid.
Okay, so now we can be confident our loss function will work even if the predictions are not between 0 and 1. That is required. All that is required is that a higher prediction corresponds to higher confidence. An image is a 3. Okay?
Not using our Sigmoid. Sorry, I'm still stuck on that. It's not using our Sigmoid function. It's calling it as a method on the predictions object,
Which is PyTorch.
which is some PyTorch thing. So I'm sure it's using the inbuilt PyTorch one.
Mm-hmm.
Yeah.
Okay. Having defined
Okay.
the loss function, now is a good moment to
Capitulate.
why we did this. I've not
Give
seen
up.
that word. After all,
Oh, it's a common word in German. Rekapitulieren.
wow. It doesn't sound German.
Do you have it's probably not German. Do you have the word capitulate too, or is it another word?
I think so.
Because in German, so kapitulieren means to give up, and then rekapitulieren means to like think about something again, or like revisit it. Revisit.
Surrender.
Oh
Capitulate.
yeah, that kapitulieren.
Summarize and state again.
Funny, huh? Just two words so similar to each other.
And yet the differences in the definition.
And yet. Element iron.
Okay. Recapitulate why we did this. After all, we already have a metric, which was overall accuracy. So why did we define a loss? The key difference is that the metric is to drive human understanding, and the loss is to drive automated learning. To drive automated learning, the loss must be a function that has a meaningful derivative. It can't have big flat sections and large jumps, but instead must be reasonably smooth. This is why we designed a loss function that would respond to small changes in confidence level.
Mm-hmm. In the confidence level of the predictions, like how confident the predictions are. If the confidence of how sure it is changes a little.
Yeah. This requirement means that sometimes it does not really reflect exactly what we're trying to achieve, but is rather a compromise between our real goal and a function that can be optimized using its gradient. The loss function is calculated for each.
That's interesting. That the accuracy and the loss function are not actually the same thing, and that you want to work with accuracy, but like it's just, if I understand this correctly, it's just more like of a proxy, but they're not necessarily all the way connected.
Mm-hmm.
Because the function, the automatic improving, works on the loss, and we kind of wanted to do something with the accuracy. Does that make sense?
Sort of. So they're different, like they're not related, but they're still attacking the same thing and getting
I think so.
Their own results.
Right. Because the problem with the accuracy was what he said, that like is either like we're doing a classification between two things, so it's either 3 or it's 7. So we have like this, it's always going to be classified as a 3 until it hits a certain threshold, then it's going to be classified as a 7. So we have this like long flat thing, then a big jump, then again another long flat thing, and then you can't apply any gradient descent on that because it doesn't know where to go if it doesn't have if the function doesn't have a, what's it called? Inclination, steepness.
Sure.
Yeah. And so it operates on something else that has a sigmoid function in the end, does it? Because we put everything between 0 and 1? No. That's unrelated.
I think that's unrelated.
Okay. But some sort of different function that actually has more of a, like that has more of a shape, function shape, so that you can find whether it's going up or down. And then the stochastic gradient descent can do something on that and can like figure out which direction it should move.
Okay. Let me...
That's at least what I take away from this one.
This is why we designed a loss function that would respond to small changes in confidence level. Okay. This requirement means that sometimes it does not really reflect exactly what we are trying to achieve. This is why we designed a loss function that would respond to small changes in confidence level. So the loss function responds to changes, okay, but is rather a compromise between our real goal and a function that can be optimized using its gradient. Right. The loss function is calculated for each item in our dataset, and then at the end of an epoch, the loss values are all averaged, and the overall mean is reported for the epoch. Okay. Metrics, on the other hand, are the numbers that we really care about. These are the values that are printed at the end of each epoch that tell us how our model is really doing. It's important that we learn to focus on these metrics rather than the loss when judging the performance of a model. Okay.
Okay. SGD and mini batches. Now that we have a loss function that is suitable for driving stochastic gradient descent, we can consider some of the details involved in the next phase of the learning process, which is to change or update the weights based on the gradients. This is called an optimization step. In order to take an optimization step, we need to calculate the loss over one or more data items. How many should we use? We could calculate it for the whole data set and take the average, or we could calculate it for a single data item. but neither of these is ideal. Calculating it for the whole dataset would take a very long time. Calculating it for a single item would not use much information, so result in a very imprecise and unstable gradient. That is, you'd be going through the trouble of updating the weights, but taking into account only how that would improve the model's performance on that single item. So instead, we take a compromise between the two. We calculate the average loss for a few data items at a time. This is called a mini batch. These are our mini batches, maybe. The number of data items in the mini batch is called the batch size. I see. A larger batch size means that you will get a more accurate and stable estimate of your data set's gradients from a loss function, but it will take longer, and you will process fewer mini batches per epoch. Choosing a good batch size is one of the decisions you need to make as a deep learning practitioner to train your model quickly and accurately. We'll talk about how to make this choice throughout the book. Another good reason for using mini batches rather than calculating the gradient on individual data items is that in practice, we nearly always do our training on an accelerator such as a GPU. These accelerators only perform well if they have lots of work to do at a time. So it's helpful if we can give them lots of data items to work on. Using mini batches is one of the best ways to do this. However, if you give them too much data to work on at once, then they run out of memory. Making GPUs happy is also tricky. All right. As we saw in our discussion of data augmentation we get better generalization if we can vary things during training. One simple and effective thing we can vary is what data items we put in each mini batch. What data items? Rather than simply enumerating our data set in order for each epoch, instead, what we normally do is randomly shuffle it on every epoch before we create mini batches. PyTorch and FastAI provide a class that will do the shuffling and mini batch collation for you. And it's called the Dataloader. Finally, there they are. So we get a bit of extra info on what a Dataloader does. A Dataloader can take any Python collection and turn it into an iterator over many batches, like so. Collation. What's a collation? Collation. Is that like a collection of things?
Where do you see collation?
I just see this COLL, but there was the word, yeah. So I assume that's what it stands for. Is it like, yeah, I think it's like an agglomeration of things, but I'm not sure. The action of collating something. Wow, that's a bad explanation.
Collection or construction of ordered systems of data from the raw data gathered. Okay.
All right. Range. Okay, so we make 15 items, 15 batches. We order it in 15 collates. We collate it. Data loader. Collation, batch size 5, shuffle through. So this is just making a bunch of random numbers, right? To experiment with
how does it
using a data loader.
How does it break it up into batch size 5 and it's 15. Got it. Okay. So if we did
so there should be all 25. The numbers from 0 to
it should be 5 of them. Yep. Okay. All the numbers from 0 to got it.
Okay, so the collation holds the data, and then we give it a batch size, and then it shuffles it and breaks it up into mini batches. Cool.
Right.
That's nice. Yeah.
I wonder, hold on.
Yeah.
What if we do something that's not, does it give us, okay.
So 1, 2, 3, does it, it discards one, huh?
No, there's
3. So 0 is not in, no,
there's 3 in this one.
All right, I see, okay. All right, so it's fine with that. It doesn't have to be the same necessarily.
Right. It's going to do its best. Okay, cool.
For training a model, we don't just want any Python collection, but a collection containing independent and dependent variables. That is, the inputs and targets of the model. A collection that contains tuples of independent and dependent variables is known in PyTorch as a dataset. Here's an example of an extremely simple dataset. make one of those fastDI lists, enumerate string sc lowercase. Okay. All the letters of the alphabet with their respective indices.
Okay.
Yeah.
When we pass a data set to a data loader, we will get back many batches, which are themselves tuples.
Nice.
Yeah. Of tensors representing batches of independent and dependent variables. So DL is data loader. And take that DS, batch size 6, shuffle true. Okay, so here, interesting. So we're getting the index in this array or this list, and then the value, the same index, but in a tuple.
And the same index, yeah, okay. Yeah,
Tuples of tensors representing batches of independent variables.
That's it. So each of them is a data set. Okay, so we pass a data set to a data. Okay.
So this is the data set.
That's a data set. Yeah, I got it. And then the batches are they just splits them into two separate tuples. Yeah. Cool. X and Y.
Oh, this is a tuple here. Yeah, tuple, and it's a tensor.
Oh, so
no,
tensor. This one is a the X.
This is here. So it's a 2-item tuple, with the first item being a tensor, with this, and then the second item here.
Just the tuple, it seems.
Is the tuple, and then inside the tensor, this corresponds to the original index of this in the data set.
Yeah.
Okay. Oof.
All right, that makes sense.
How do we feel about putting
it all together? 64 cells. How are you holding up?
I think I need to make some coffee, but
I'm up for going some more.
We're an hour.
An hour 40.
So what do you
put it all together? I'm up for continuing. I'm still
okay.
Bright and alive. Enough. Less tired than last time.
Cool. All right.
Less math.
Let's do
to
it.
tire me out. All right. Okay, let's put it all together. It's time to implement the process we saw in code. Our process will be implemented something like this for each epoch. For XY in DL. So DL is our data loader. For XY are these two tuples of one being a tensor, the other one being just a tuple of target labels. For XY data loader, predictions model. Apply the model to the X to the dependent variable. Is that right? Is that a dependent variable? Loss function prediction. Why? Okay, we compare the actual predicted results with the labels. Then we do backward. We learned something about that. Backward being the get the gradient, I think.
Yeah.
And then it was like writing something about, parameters minus equals parameters dot grad times LR. I don't know what's that about. Parameters gradient times loss times LR. What's LR?
This seems like I'm just gonna go ahead and say I think this is just gonna be, because this isn't even something that you can run. So
You're
I
right.
think we're just gonna let's just continue on.
First, let's re-initialize our parameters. Weights, initialize parameters, 28 times 28, size of pixel thingies, 1. Bias, initialize parameters, 1. I'm not sure what this 1 is about. A data loader can be created from a dataset. Data loader, dataset. Where's our dataset? Batch size 256, XB, YB, first data loader. So that's the first. What's first? I have no idea.
XB.shape YB.shape.
YB.shape.
Well, there's that 256. And then what is this?
Batch size. Yeah, we gave it the batch size. 2784.
Oh, is this?
So 784 is how many? No, I don't know what it is.
No. Is this? I don't think it's this. Oh yeah, there we go.
What did you find?
So 784 is 28 by 28.
Huh.
And that means 1 is... I forgot what this one meant, what the second item in this.
Yeah, me too.
Anyway.
Was it? No, there was something about it being the... no, this is not it.
This isn't
like
the rank size, right?
It's not I was just wondering the same, yeah. But that would be really high, very ranky, 784. No, you could try that actually. You could do xb.rank. And I think then it's going to say 2.
Come on. Oops. Oops.
Tensor has no attribute. Huh. I thought it did. Was it always shape?
It's annoying that these are all...
You can start typing if you want to go R or something. Requires grad. Okay, so yeah, I thought we could do rank. I thought we ran something with rank. Guess we didn't.
I thought we did too, but anyway. So let's do the same thing. Batch size of 4. So 784. Yeah, this is saying the same. So valid D set. I don't know where this is. You know, where's D set?
Yeah, I was wondering that too. It feels like, can you search for it actually? Because maybe this is something that we defined really high up.
Oh, this is the one that we just defined earlier today.
Ah, that's the one we zipped. Okay.
Yeah.
So that's a zipped training set and training labels. Okay, yeah. All right. That's what we just learned. That's what a data set is. A tuple of, like, zip creates a tuple. So we just have all the images and all the labels. Okay, that's our data set. Sure.
Okay. Yeah, and this was, I remember this was up there too. Okay.
Okay. Size 4 for testing. 4, and maybe this is actually a rank.
This is the batch size.
4. No, the batch. This is one batch. No. Yeah, and the batch size is 4. So we get 4.
Is the mini. Yeah, let's create a mini batch. So the batch size here, because they were saying 256 is the same. 256, 256. Right.
We're gonna split 256 up in batches of 4s, but 784 stays the same. So maybe that's like the.
This is that 28 by 28 thing.
Mm-hmm.
Okay. So loss is the... Okay, so now it's going to predict the loss.
MNIST loss predictions train Y The first 4.
That's that mini batch.
Wait, what? So it assumes that the first. This is actually how it splits it up. The batches. It actually takes the first 4, or what?
So in this case here, right, we're defining a batch as the first 4.
We're taking the first 4. Gotcha. Yeah. Okay. And so it's also for the labels. It's going to be the first 4.
Linear 1 using that batch, and then so that's what preds is now, and then you're training on those 4. Yeah.
Well, this is just the labels, the train Y. You're just checking, comparing. Yeah. Loss backwards. Now we're back propagating and getting weights.grad.median. Okay. We're just flying over this 64, huh? Soaking up all the knowledge.
Well, so I think as
no, I'm fine with moving on. I'm just joking.
Because like part of this also, like, I don't know, for me learning this stuff, I also need to like see everything put together, and then I would be more comfortable like going back and understanding this. So right now, I don't know. We're flying,
we'll see.
But you know,
it's all good.
This is machine learning, right? We're easy stuff, easy peasy.
We're meant to fly.
Yeah. All right. So it's calculating the gradient. So just put everything together. So the preds is the model,
applying the model to XB.
The loss, MNIST loss, the other function, taking preds and YB and then loss. Okay.
And the labels.
Got it. Okay. Okay, so different results. Actually adds the gradients of loss to any gradients that are. So the gradients have changed. The reason for this is that loss data backward actually adds the gradients of loss to any gradients that are currently stored. So we have to set the current gradients to 0 first. Okay. In place operation methods in PyTorch whose names end in an underscore modify their objects in place. Okay, so .0 underscore. For instance, got it. Our only remaining step is to update the weights and biases based on the gradient and learning rate. When we do so, we have to tell PyTorch not to take the gradient of this step 2, otherwise things will get very confusing when we try to compute the derivative at the next batch. Okay, so if we assign to the data attribute of a tensor, when PyTorch will not make the gradient of that step, here's our basic training loop for an epoch. Okay, train epoch. Model, LR params.
Sorry, for me it was cutting out a bit.
It's so sometimes just so like these Jupyter notebooks. Sometimes they're like great, but like, man, not having this variable like just there, so you could just see it. You have to like scroll with all this text. So messy sometimes. Anyway. Just a personal rant. All right.
So for me it was cutting out a bit before. I'm not sure. Is there anything I need to...
No, of course not. We're flying, Martin. Of course not.
Maybe we should have stopped before.
No, I just want to see how all this is kind of coming together.
Let's do that. Let's go to the bottom and figure out what's going on, or just go. I'll let you just scroll over it, and
I just want to skim.
I'm just gonna have it skim by. No hands.
Learn
brain.
Fast. No brain.
Just get it in and out again.
All right. So we also want to check how we're doing by looking at the accuracy of the validation to decide if an output represents a 3 or 7. Okay. So now we're going to check this. If it's a 3 or 7 on the first 4. This is the same thing, yeah. Regulation, accuracy. xb.sigmoid, so this is their built-in Sigmoid function, correct? Okay, and then this is the same.
Oh, we unfurled higher up.
Except here it's 0.5, so it's saying, yeah, got it, because it's either 3 or got it. Okay. We can check it works. Batch accuracy, train y. 0.25.
What was it before?
No, I'm just like, it makes sense because this is 1 of 4.
Right. 1 out of 4, yeah.
Yeah. Okay. So now.
Batch accuracy. So we're running this for. Again, we're broadcasting and running it for all of them. Applying this function to each epoch. Is that true? Validate epoch to each batch. For 1 epoch. All right. That's our starting point. Let's train for 1 epoch and see if the accuracy improves. It does. Look at that. It's going to get much better. Chip. 0.97.
Nice.
That's decent.
Mm-hmm. I wonder. Oh yeah, because it starts at 9.7.
What? Because you ran it again?
Yeah.
And 759 and 784. 9798.
This must be like, yeah, we're getting like super,
we're getting
super,
in the
super
curve, yeah.
tiny. Okay, cool. All right, so we're already about at the same accuracy as our pixel similarity approach. And we've created a general purpose foundation we can build on. Our next step will be to create an object that will handle the SGD step for us in PyTorch. It's called an optimizer. Okay, so creating an optimizer.
Okay, because creating an optimizer, because it's such a general foundation, PyTorch provides some useful classes to make it easier to implement. The first thing we can do is replace our linear1 function with PyTorch's nn.linear module. A module is an object of a class that inherits from the PyTorch nn.module class. Module is an object of a class. Okay. Objects of this class behave identically to standard Python functions in that you can call them using parentheses and they will return the activations of a model. Okay, and then linear does the same thing as our init params and linear together. It contains both the weights and biases in a single class. Here's how we replicate here's how we replicate our model from the previous section. Linear model equals nn linear 28 times 28 1. And that compares to, what did we do before? It said it replaces the init params and linear function. Okay. Every PyTorch module knows what parameters it has that can be trained. They are available through the parameters method. WB weights and bias equals linear model.parameters. So we call the parameters method on linear model, which is one of the nn.module class, and then it has access, like it knows about its weights and biases, I guess. Weights.shape, bias.shape. Scroll, please. Gracias. Every PyTorch module knows what parameters it has that can be trained. I just read that and it flopped out of my head. I thought you just scrolled a bit further, but you didn't. All right. We can use this information to create and optimize. Okay, so, but I guess the gist of this thing that I just read half-mindedly was just that there's this models, like you have a models class in PyTorch, and you can inherit from that, and it has a bunch of models already in there, and all of them know about their parameters. They all have this parameters method on them that you can call.
Okay.
Fine. And now we can use this information to create an optimizer. Class basic optim. We're gonna initialize it with parameters and LR. What is LR? Learning ratio? What's LR?
We had.
I think we've seen something like that before. I also didn't get it back then.
LR over here.
There it is. What is it?
1.
Linear LR learning params.
It's just
Learning
set to
rate.
1.
Set to 1. Of course it is set to 1. Okay, move on. Maybe it shall explain itself.
Did you want these like this?
Oh, you want to clean it up for me? I appreciate that very much. Well, but then come on, clean it up properly. Or don't. You could just in the init function, you could method, you could put the parameters into new lines. It doesn't matter.
Like this.
Well, then you gotta have to then self.lr points to lr and list params points to self.params.
Is this
See,
what
not
you
too
want?
easy. No, that's not what I meant. All right.
What do you want?
No, I don't want anything. I'm happy without any wishes. You know, all zen today, as I said. Step.
No, but how would you clean? What do you mean? How would you clean this up? Self.params.
Self.params equals list params. Self.lr equals lr. It's just this double assigning values to Python variables is not a very nice way to do it, because it's kind of confusing. Because you got to know that the first one goes to the first one, the second one goes to the second one. So generally, it suggests that you put each of them in their own line. That's all.
Got it.
Like,
I think the same. There's a similar notation in Go also, so this makes sense.
Yeah.
I'm gonna leave it.
Fine.
All right. So we got the step function. We have 0 grad.
We're trying to So he's trying to code an optimizer here.
We can.
Okay. Yeah. Basic linear model parameters. Again, LR is here. This LR is something. We defined it somewhere.
It's
what
set
is
to
it?
1. It's just.
Why do I not know what it is?
It's just one dot.
Well, what is that? Learning? Is it learning rate? I mean, it's got to stand for something, right? Can you search for a learning rate? Maybe it tells us that this is what it is. Stepping with the learning rate. LR. Oh. Whew. Okay, so our learning rate is the steps that it takes, and we gotta pick the right learning rate for it to not fail and explode inside of our heads. And the right one clearly is 1.0. What are you looking for?
Give me something to just.
Something classy.
No, what was the thing? What was it called?
What was you looking for?
I just didn't want to do all this scrolling. I was trying.
You wanted to go back.
What was the function called, or the class, or I don't
know. Wait, it was. You can do a capital linear, capital linear. That's close by. It's still worth it. It's still a bit to go.
Okay, hold on.
Capital L dot linear.
Oh, L dot linear?
dot L linear. Yeah, there you go. That's pretty close.
All right.
Right?
Yeah, I was thinking of basic.
I know, but I didn't remember that.
Yeah. I could have also just searched for this. I'm sure this is the one of the only ones on this line.
Probably.
Okay, so we ran this. Our training loop can now be simplified to train epoch model for XBYB in Dataloader, calc grad XBYB model. Okay.
Optimize. Use our optimizer to step.
I'm
Well, what
just-
does the step method do it again? I know you're just
Just can't do this.
just
this way.
absorbing it. Oh. What you doing? You want to put it into one line. You're gonna make me cry.
Can you do that in one line? All these function calls?
No,
No, right?
I don't know.
I'm just not gonna run it again. I'm just gonna leave it like that to confuse us for next time.
That's horrible. Yeah, it's too easy anyways, these topics. We gotta spice it up a little, right?
All right. So let's put our little training loop in a function to make things simpler. So train model for, okay, so train epoch. That's this one.
Ah, you should run it.
Fine. I'll run it.
Clean up, clean up.
Fine. I'll
Beautiful.
put it back. All right. So validate epoch model and okay, so let's run this. So this is doing, so if I run it again, so all right, so we started at 4.9 and we ended at, oh wow,
And 7.8. That's
pretty good.
much. Yeah, that was like after running it 30 times.
Yeah. And we had 9814. Okay. Okay.
FastAI provides SGD class, which by default does the same thing as our basic optim. SGD.
That's this. Opt equals SGD.
Yeah, now it just, instead of the custom class, we're just using the one that they already have. FastAI also provides learner.fit, which we can use instead of train model to create a learner. We first need to create a learner. We first need to create a data loader. No S, by passing in our training and validation data loaders. And we need to create data loaders by passing in our training and validation data loaders. Is there like a thing, should we like, if we come up across any typos, is there any place to send them to?
Maybe like, is this on
It's
their
it's on GitHub.
Yeah.
Yeah, we could probably just make a PR or something.
Yep.
Create a learner without using an application such as the CNN learner, we need to pass in all the elements that we've created in this chapter. The data loaders, the model, the optimization function, which will pass the parameters in turn, the loss function, and optionally any metrics to print. Learner. Now we're using the define thing, passing it to data loaders. Data loaders. Why is this plural? What were the data loaders? Did we just do that? Can you just scroll a tiny bit up? Data loaders, there it is, data loaders. So we're passing it one data loader and the valid data loader. What's going on here? Magic. Loaders. Path device node. Basic wrapper around several data loaders. So it's okay. What's the valid DL?
That's the other data loader.
So it's just two data loaders. We just have two data loaders.
Yep.
Okay. All right.
Okay, so to create a learner without using, we did this already? No.
I just read it, but it seems like I didn't understand anything about it, so maybe we should just read it again.
Sure. To create a learner without using an application such as CNN Learner, we need to pass in all the elements that we've created in this chapter. The data loaders, the model, the optimization function, which will be passed, so the optimization function will be passed the parameters, the loss function, and optionally any metric to print. Okay, so learn is this learner. So the data learners,
Loaders.
The learners. This is the, what is this? The model.
That's the linear function that applies linear transformation to the incoming data. Whoa.
Okay.
Yeah.
Well, this seems familiar.
Oh, we're doing something. Learn.fit. Yeah, I do remember that.
Okay. So learn.fit 10 LR.
Learning rate equals learning rate, which is 1.
Okay, so the training loss from 0.63 to 0.01.
Good.
And the batch
accuracy goes
pretty high, yeah. Okay. As you can see, there's nothing magic about the PyTorch and FastAI classes. Isn't there, though? There's a little bit of magic going on.
A little bit of magic. Feels a little magical to me.
They are just convenient prepackaged pieces that make your life a bit easier. I don't know about you, I need to review this as like a comparison. Now, like understanding that the whole purpose of this was to show not really how to build it, but like this is what PyTorch comes out of the box, and this is how you could build those things. Mm-hmm. I think now I understand, okay, this is how all these pieces kind of come together, and then you were explaining how to build all of these pieces if we didn't use PyTorch. So,
mm-hmm.
Cool. What is this non-linearity? Oh wow, we're almost done. Well, done.
Scroll to the end. Let's see what's going on in here. I think just as a quick overview. That's the activation stuff. I think relu is some sort of activation function stuff. This looks like it's still got some meat in it, huh? What do you think?
Let's
scroll. Keep going to the end. Let's see.
Oh boy. Okay, we're not showing 40 lines.
Whether we still have the brains for that today. Okay. Going deeper.
This is just more magic.
More magic.
He said it wasn't magical. Now it's magical.
It's rather magical. It's different. So, what do you think? I'm not very attentive anymore. My brain's kind of like fizzling out.
Yeah.
So
I'm kind of fried.
I'm up for calling it a lesson, and then maybe doing this last part. Like maybe we could do like a high level revisit, and then this last part, which is rather short, for next time. Or we really, because we haven't really built anything for a while, maybe we just try next time to build something and weave this in a bit, something like that.
So I mean, this is obviously very specific to the MNIST stuff, but I think we did build like the classifiers that we already built use these predefined PyTorch, right? Like now we're just getting in. It seems like the structure of this is like, all right, build this cool thing with a ton of like abstraction and magic. Now you're gonna learn that it's not really magical. These like we're gonna pick apart the layers. So I don't think it, like if we build something, we're not gonna build it with this.
True.
Right? We're gonna build it with the magic again. This is kind of, I mean, because like I don't think, for me anyway, right? Like I don't really understand this enough to build something from it. We could try it, but I would also want to do it like in a fresh, blank Jupyter notebook.
Yeah. No, I mean, this is the whole baseball story, right? Like we should probably play a little more baseball before we actually properly learn the rules, right? Because we've played around a little with the models and this was fun and we built some stuff, right? And we kind of understand how it goes. And now we're looking at this is us looking at the rule book essentially.
Mm-hmm.
And maybe it's interesting, but maybe maybe it's still a bit too complicated for me, at least.
What if we revisit one of the?
That could be fun, yeah. The ones we did already.
The thing we did already, and then try to just take some of that magic away, and we build our own, like replace some of the magic with our own, so that we can better understand what we just learned today, or
I like that.
Sort of learned today, maybe.
Yeah, let's try that. So we're gonna have like both notebooks open, this one and the one that we're working on, and then just compare and see whether we can match stuff to understand what is what.
Yeah, that sounds good to me.
Yeah, cool. I like that too.
All right, so let's end this stream here. And Friday.
Next plan for Friday is up.
See
All right.
everybody on Friday.
Bye.
Bye.